combining social media images and bitemporal satellite images for automated detection of damaged areas after flooding.
Hello everyone, my name is Jiaxi. I'm a master's student in the Division of Sustainable Energy and Environmental Engineering at Osaka University, Japan. And it's my great honor to present and share our team research progress with you. I hope you understand our content and sincerely invite your feedback to help us conduct the research. And let's get started. My topic for today's report is combining social media images and bitemporal satellite images for automated detection of damaged area after flooding. And this report will be divided into 6 parts as shown here. And first is our background. As climate issues intensify and urbanization progresses, the hazards from extreme weather events are becoming increasingly severe, and this research focuses on discussing the assessment of flood damage to buildings, highlighting the labor-intensive and time-consuming drawbacks of traditional tools. And currently, deep learning becoming a strong tool to tackle such professional challenges. In reviewing previous work, we focused that since 2018, studies have been applying deep learning to the change detections. Change detection involves comparing satellite image from 2 different times, so we see it's the same to the disaster assessment before and after. And in the literature review, we found that some studies has begun to apply deep learning to disaster-related areas. For example, King et al. Used the ResNet 18 and Chen et al. Employed CNN models. And however, research in this field of disaster still relies on outdated models to assess building damage. And traditional simple models can achieve preliminary application levels when applied to overall data. However, when observing the performance in specific items, such as in flood events, there is a significant decrease in the performance. For instance, Kim et al. Obtained an overall model's performance at 85% when investigating various water-related disasters, such as hurricanes, flood, and tsunamis. And however, the accuracy sharply dropped to 23% when focusing on the flood events. Therefore, we speculate that this decrease in accuracy is due to the subtle representation of flood-induced damage to building in satellite images, and making it challenging for relatively basic models to identify such complex features. And the research question has shifted to how to improve the generalization performance of the models in disaster detection domains. In current research, using single model data as input is a traditional approach, but multimodal learning is an effective way to enhance the model's generalization, which has been relatively underutilized in disaster change monitoring. And for instance, Shin et al. Utilized the street view images and satellite images as multimodal inputs, and while Kahawa et al. Employed area images from various angles as multimodal inputs, both achieving certain improvement effects. Therefore, this research aims to incorporate multimodal learnings into the research within the disaster assessment domain. Under this prerequisite, suitable dataset for training are necessary. This research chose 2 different modalities of data, the social media image dataset incident 1M and the satellite image dataset XPD to train the models. And so here comes the objective. And generally, the common approach to improve the generalization of the model is to provide more data. And however, the direct annotation cost of satellite images is unacceptable for us. Therefore, since fundamentally increasing dataset size helps the model remember more valuable information, this research used a large-scale social media disaster-related dataset as supplementary data to enhance the model's performance. So the objective of this study is to enhance the generalization performance of state-of-the-art change detection models in downstream tasks of disaster assessment. The contribution of the research lies in leveraging the low-cost social media data to improve the model's capability to recognize disaster-related informations. And here is the proposed method. And the first step is to collect flood disaster-related data from social media datasets. And the second step is to obtain the disaster informations in the social media images by training the deep learning models. And the third step is to insert the disaster informations on the BIT modified models and train by the Midwest flood dataset. Okay, and here is the process of obtaining the required social media dataset related to plotting. Firstly, the instant 1M dataset provides approximately 1 million disaster-related social media images, and a pre-trained resident 18 models was utilized to filter out images depicting flood events. And this approach is the finding of the Weber et al., who employed the pre-trained resident models for the annotation and training for disaster images. Finally, the acquired dataset of flood images serves as the training set for the feature extractor. And this is the process of obtaining the satellite image dataset. For this experiment, satellite images relevant to the Midwest flood events from XBD dataset were utilized, and through data augmentation techniques, the dataset was refined and used to train the BIT-modified models. And here is our model architectures. This research designed a feature extractor to extract the disaster-related information from social media images and successfully integrated it into the BIT-modified models. Additionally, attention mechanisms were employed within the models to enhance the focus on disaster areas, thereby improving the overall model's performance. And next, the feature extractor is modeled after the encoder of the BIT models because the parameters can only be loaded into the main model if the structure is the same. So the parameters were passed in the convolutional layer of the pre-trained CNN models to the BIT modified models for initialization. And next is the experiment result. The model was developed using the PyTorch framework and trained for 200 epochs in NVIDIA RTX 8000 GPU. And the graph illustrates the trend of loss and F1 scores throughout the training process, as well as the model's performance on the validation set. And it can be observed that 200 epochs of training have enabled the models to achieve stable performance, and indicating that training conducted is sufficient. And these are the results of each benchmark models on the test set. For this experiment, F1 score and parameters volumes were employed as key evaluation matrix. The F1 score reflects the model's detection capability, with higher values indicating the models have stronger detection abilities. And the parameters volumes represent the deployment difficulty of the models, with higher values indicating greater challenges in deployment and applications. And these are the final results of the models. The proposed method, in some aspect, has better performance. And compared with the original BIT models, all the metrics are 1. And the BIT modified model keeps the advantage of low parameters volumes, which means the model parameters including more critical informations. And the second evaluation dimensions involving visualizing the prediction results, it can be seen that the model shows advantage in both false positive and false negatives. The false negative is incorrectly predicting an undamaged building as damaged, and the false positive is incorrectly predicting a damaged building as undamaged. And next is the result analysis. The left figure illustrates that the modified models can identify more damaged area compared to the original one. And the right figure shows the BIT modified models achieved performance comparable to the SOTA method to some extent. And to analyze the internal framework of the models, we also employ the method of class activation mapping to visualizing the intermediate layer of the models. It can be observed that the modified model convolutional layers are more adapted at detecting damaged building more quickly and less susceptible to interference from irrelevant information, such as land and vegetation. And final is the conclusions. And our flood damage assessment method, integrating bitemporal satellite and social media images through deep learning techniques, showcased a significant 2% increase in F1 score compared to the original models, and the proposed models balance the performance and computational resource, ideal for swift disaster response. And despite this progress, limitations arise from insufficiently annotated data, confining experimental validation to the Midwest flood dataset. And thank you for your attention. If you have any questions, please ask.
Thank you. Question? Okay, I'll ask a question. So, if I understand correct, you're using the social media data and the satellite data to train your model. You didn't quite get, the outcome you had hoped for, but it's going in the right direction. But if the model was, showing, I mean, if you want to use the model, you would then use it only on satellite data to understand what is, which are damaged and which are not damaged. Is that correct?
Yeah.
Okay. All right.
Yes. That's correct.
Yeah. So then the only point is that after a flooding, satellite image, and then you can quickly discern what are the damages that were done in the area, where help is needed, and things like that. So for quick reaction after flood disasters.
Yeah. Yes,
Yeah.
it's for quick response to the after disasters.
Wonderful.
Yeah. Thank you.
Any other questions? Okay, there. Yes. Sure.
Thank you so much for that presentation. I think we're all still mulling over how much information you've given because it's such valuable research. I'm going to ask my question. It might be a bit high level, but in combination with what the previous presenter showed in terms of predictive element of trying to assess where floods might be an issue, I wondered if you have a component in understanding where there might be infrastructural vulnerabilities, so that if a flood is to happen in this area, it's of higher risk of maybe having more catastrophic events coming forward, and then more help needs to be sent into that area. I wonder if that's an element that informs your research.
Okay, thank you for questions. And I think you means how to predict the area's risk levels by using this research. I want to mention that in this research we only focusing on the existing damage. So is that helpful to understand the future risk? Maybe it needs another investigations about this, how to combine the building damage to accessing the risk of this area. So it's need more serious support this. So in this research, we didn't answer this kind of questions. So it's a very interesting extent in research in the future, maybe. And thank you for questions.
But maybe a related question is, what's your next step?
My next step may be more focusing on the structure of the models and try to how to utilize, because it is a time series to focusing on the change detection. We all know that deep learning is in computer visions are dealing with the pictures, and the more picture we have, like the time series, we only have 2 times right now. So maybe there are some existing series that when you're dealing with more images in this time series, you may have more processing you can do to get more complex structure of the models, and that's what I'm interested in. Yeah, thank you.
Wonderful. Thank you very much. You have a question? Sure. You can have one more question.
Okay, sorry. Yeah, I think it's a very interesting study, but I just want to wonder, because when you talk about the social media pictures, so sometimes, for example, in areas with a lot of people, then same event, easily we can trigger a lot of people to take a lot of pictures. But in some areas, maybe less populated, then maybe we have less. So how to handle this kind of maybe information imbalance? And then, for example, with some areas or some instances with lots of pictures, when you remove duplicates, because maybe it's a little bit computational heavy to handle so many pictures actually describing the same event, then maybe removing them because they're describing the same thing. And also another question is, when I look at the result, then it seems that your precision is above 70-something%, when your recall is only like 20-something%. So recall 20-something%, it means that majority of the events still cannot be identified. So how to address this one? Thank you.
Thank you for your questions. And for the first one, you mean how to deal with the bias of the data distributions. Okay. In our research, we only focus on the disaster element in the social media images, and it's relevant similar to like the bricks and so on, and the bricks and so on in the social media images. And we only extract that elements from the social media images and transfer it into the satellite image models. So this is maybe after we figure out what informations we extract from the social media. That is important. If we focusing on some different elements in different areas is the key information in the social media images. If in this scenario, only if this scenario happens, we should focus on the distribution of the social media image distribution, I think. But right now, we didn't figure out the basic theory of the information, what kind of information we got from that data set. So it cannot be tell you right now. So maybe it's a very interesting research in the futures. And for the next one, you mentioned about the recall matrix, and it seems like you cannot extract all the damaged things out because the existing open source data set only have several limited examples. So all we know, the data is the most important things in the deep learning, right? So it's very regretful to know that it's the limitations of the open source data set. If we could get more accurate, more balanced data set, it will be increased. Yeah, I think. Thank you. Yeah, thank you.
Thank you very much. Okay. We